Okay, so for the benefit of those who just joined us, we are given a list A, and we would like to sort it. And we have the idea of doing this using recursion. And so when we do things using recursion, there's sort of two things that we need to do. One is to think about, and this is the part that I like to do, that I always jump to, is to think about how to break the problem up into recursive subproblems, or subproblems that we can solve recursively, smaller problems we can solve recursively. And the other thing, which is actually just as critical, but the one that I always skip, is we should think about what are the base cases, what are the easy cases. So for sorting, so you give me a list A, and I want to sort it. When is it really easy to sort a list? What kind of list is really easy to sort? Yep. One with one element, and just as easy as one with 0 elements, right? Then there's nothing to do. If there's only one element, well, there's no reordering to do because it's the first and last element of the list, no matter what its value. So we have some sort of easy stuff we can do. So if the length of A is less than or equal to 1, then what we can do is return a copy of A. Okay. So a copy of A from the beginning to the end, which just means another list that contains 0 or 1 elements. All right. So now we get to the fun part. And on the sort of the surface of it, this sorting thing sounds, it sounds like a complicated problem, right? I give you a list with a bunch of things, they're in some arbitrary order, and I want to output them in sorted order. So let's think about how we could do that. And let's think about that through an example. So there's an example of a list, and I'd like to sort, and I'd like to somehow sort this recursively. And the nice thing about that is all I have to be able to do is break this into 1 or 2 subproblems on a smaller list. Recursion will handle those, and then glue things together there. So let's try something simple. Let's just take the first element of the list, 11 in this case. So what is the list after it's sorted, or when we get in the end, what do we want to return? In that thing that we're returning, 11 will appear somewhere in the output, right? And the thing that we return should have all the same values that are in the list we're given. So somewhere in the output, we're going to return something that looks like this, and 11 will be in there. What's going to come before 11? You can just tell me in this example. In the sorted list, what's going to appear before 11? 17?
Sorry, 5.
5 will appear before 11. Anything else? So 5 definitely appears before 11. Any other things? 2? Anything else? Everything else is bigger than 11, right? So somehow at the end of this process, I'll have 5 and 2, they should appear over here before 11. Not necessarily in this order. And what's going to come after 11? There'll be a 16. What else? 17. 98, 23. So that's 17, 98, 23, 66. Anything else? That's it. So that's everything in my list. So what's the distinguishing feature of these ones that appear before 11? Why did they appear before 11? What's the rule that you use to say that they're going to show up before 11? Less than. They're all less than 11. And these ones? They're all bigger than 11. All right, so let's see if we can turn that into some code for sorting. So what was 11 here? Well, 11 just happened to be the first element in my list. And I know that that first element exists because I already made sure if there was no first element, if the list was of length 0, then I would have returned already. Okay. Now, in the thing that I want to return, first thing I want is all of the stuff that is less than 11. Not x, let's say y. And so that'll give me a bag of stuff, which is, or a bunch of stuff, which is smaller than x, the thing which was 11 in this example. But I don't want it in any order. I want it in sorted order. So how do I sort it? So the answer is recursively. I'm writing a function that sorts things, so let's sort this thing. So what this should give me then, in this example, is 2 and 5. Okay? Now, I want to put the value, what should appear next in the sorted order is 11. I have to be a little bit careful here because I don't know that all the elements, unlike this example, that all the elements in this list are distinct. So for example, the value 11 could appear many times, but I know how to deal with that. That's just looks like that. Okay. So I sort these things. This bag of things, that gives me this. I take all the copies of 11, all the things that happen to be equal to 11, and then all that's left is to add this thing, append this thing at the end. Okay. So, is that going to work? Who thinks this will work? Yeah. Yes? Good. Okay. So that's one person thinks it works. That means that n minus 1 people think that it won't work. So one of you who thinks that it won't work, raise an objection. Tell me what's wrong with this. Too easy? Okay, so no objections. All right. Well, before we run it, let's think about the things that could go wrong. Well, when we do recursion, we have to make sure that it's finite, that it doesn't run forever. And in examples like this, where we're working on a list, what we'd better make sure is that the list that we recurse on is smaller than the list we started with. So I have this one list of things which is smaller than x. Now, is that smaller than the list I started with? Yeah, because it doesn't include x. So even if everything was smaller than x, this list over here doesn't include x. And then there's a list of things that are bigger than x. That's another thing that I'm recursing on. That's what that third line is doing. Is it smaller than the original list? Yes, because it doesn't include x either. So that should work. Both of those things should be getting to smaller and smaller lists. And if they ever get down to a list of size 0 or a list of size 1, well, then they're happy. They will correctly sort that. So let's just check it out. So let's say A is all right, so there's my list that needs sorting. It's definitely not sorted right now. So let's try and quick sort it. And there it comes out in sorted order. I mean, that seems almost like magic, right? We know almost nothing about sorting. In fact, it seems like we didn't even do anything here. I mean, how does this thing work? All I did was said, okay, here's a couple of smaller things you need to work on. Go ahead and sort those, and it just happens for us. Okay? And so mathematically, the reason that works is the principle of mathematical induction, which translates in programming to recursion. If you're able to solve problems of size smaller than n, and you're able to combine the solutions to those problems to get a solution to a problem of size n, then you can solve a problem of any size that way. Okay. So any questions? Yeah?
I don't know if I can express this question very well, but how do you know when you're going to call quicksort there, when you're writing the function?
What do you mean?
Sorry, when you're writing your return statement there,
Yeah.
you put quicksort in there
Yeah.
twice.
Mm-hmm.
How do you know that that is where to put that statement bottom? Sorry, I'm not expressing it very well.
Okay, so do you want to know what order these things are called in?
Sure, yeah.
Okay, so what we're really doing here, that return statement abstractly looks like this. Where A and C here happen to be calls to quicksort. So I happen to know that in Python, when you have two operators at the same level of, like a string of operators at the same level of precedence like this, it just evaluates them left to right. And so that means the first call to quicksort, which is the one that calls on things less than x, will happen first, and then the second call to quicksort will happen next. In fact, what will happen is there will be a recursive call to quicksort on the first part. Then the list of things that are equal to x will be constructed. And then there will be a second call to quicksort on the right part. Okay. Not that that matters, because you would get the same result either way, but that's the way it happens. And, here's a chance maybe for me to expose my ignorance, because we can actually just see what's happening, right? At each invocation, we can print A. No, that doesn't work. Okay, so there's our random list. Let's call quicksort, but now it's going to print out all of the arguments that it's given. And here they are. So initially there's a call to quicksort on the whole array. Then there's a call to quicksort on all the values less than 5. Then there's a call to quicksort on the empty list. Why is that the empty list? Where did that call come from? Let's trace it out. Five 0 8 4 7 6 9 2 1 3 4 7 6 9 2 1 3. So first thing we do is we take x equal to 5 and we make a call on 0 4 2 1 3, right? So that's the first recursive call. What happens next? So at this point in time, we've done this splitting of we've extracted the list of things that are smaller than a 5, and we recursively call this thing. So the picture with stack frames looks like this. There's one stack frame where A equals this. And now we've made a recursive call. And in that stack frame, A is this list. What happens now? Yeah?
Because there's something smaller than 0, whatever.
Exactly. So in that stack frame, we set x equal to A at 0. So I should even put that here. In this upper stack frame, x was equal to 5. In this stack frame, well, we print the thing. We check that the length is less than or equal to 1. It's not. So we end up at this line of code where we set x equal to A at 0, which means x equals 0. And now we pull out of this array all of the things that are smaller than 0. And we recursively sort that. But that is the empty list. There's nothing in this list that's smaller than 0, right? So that's why right here, this third thing that we see is the empty list. It's only things that are smaller than 0, and that's none of them. Now, that immediately returns, which means we're back up in this stack frame. This one has gone away. And now we're going to sort the list of things which are bigger than 0. And that's 4, 2, 1, 3. Okay. And from there, 4, 2, 1, 3, we pick 4 as the thing that we're splitting around, and that gives us 2, 1, 3. Then we pick 2 as the thing that we're splitting around. That gives us 1. And that's a list that's already sorted. Okay. So that returns immediately a list that contains 1. You can put down the return values. And what does this thing do? Now it has to finally something gets to make, this gets to make its second recursive call, and that is the recursive call on all of the things that are bigger than 2, which in this case is only 3, which returns immediately a list containing only 3. And what does this thing do? Well, it adds together the list containing 1, the list containing 2, and the list containing 3. So it returns 1, 2, 3. Okay. And this one has to recurse on all of the things that are bigger than 4. And that's nothing, right? Because 4 is the largest thing. This immediately returns an empty list. And now this thing has made both its recursive calls. So it takes 1, 2, 3, plus the list that contains 4, plus the empty list, and gives 1, 2, 3, 4. That's what comes out of here. This whole part is done. And now this one has both of its things done. It has the empty list, plus the list that contains 0, plus the list that contains 1, 2, 3, 4, and that's 0, 1, 2, 3, 4. And then we're off to that side. Okay? So, and that's where this print comes from. This is the first time we got back up, the recursion got all the way back up to the first call, and now it's doing the right side of that first call, all of the things that are bigger than 5. Okay. It's really incredible, this thing. We know nothing about how to sort things, but somehow all we had to figure out was, let's just take one element and make sure it goes in the right place, and worry the other stuff that's smaller than that, we'll deal with it recursively. The stuff that's bigger than that, we'll deal with it recursively. Okay. This is a very famous algorithm. You've probably heard of it. It's called quicksort. It was invented in the 1970-something, maybe 69, I'm not sure. Really clever algorithm. The only thing that I will, maybe we can, this is a good introduction also to efficiency. So is this a fast algorithm? Must be fast, otherwise why would it be called quicksort? Well, we can test it. So let's say A has 100,000 values. Let's shuffle A, and we'll just look at the first 50 elements in A just to see that it looks kind of random. Yeah, there's a list of 100,000 distinct values, and this looks like it's random. So definitely not sorted, not in good order. And let's say B, because I don't actually want to see 100,000 things sorted, is what I get from quick sorting A. And watch it. Oops. Should have removed that print statement. Thousand. All right, so here we go. Done. That's fast, right? That seems like it. And we can check. Let's check the first 50 elements of B. Let's check the last 50 elements of B. Yep, that looks like the elements 0 through 99,999 in sorted order. So it seems to have sorted both correctly and quickly. So, and we tested with 100,000. That's good. I mean, we can even redo that with 1,000,000. Takes a little longer. That took about 5 seconds, but still not bad for sorting 1,000,000 elements. So is this an efficient algorithm, do you think? Well, let's see. Let's try a list of 2,000 elements. Is that going to be slower or faster? Or something else? Faster? So 1,000,000 elements took about 5 seconds. 2,000 should be like that, right? Who thinks it's going to be fast? Who thinks it's going to be slow? Who takes option C? Option C. It doesn't work at all. What just happened? Well, what does our array A look like? What is this array A? What's different about this array A versus the one that had 1,000,000 elements? It's already sorted. I didn't bother shuffling this one. So then let's think about what quicksort does with this array. Here's this array with 2,000 elements. We call it with A equal to this. So x is equal to the first value in A, 0. We extract all of the things that are smaller than x, and we sort those, but that's an empty list. So we come back up here, and now we extract all of the things that are bigger than x. What's that list look like? That's 1, 2, 3, up to 1999. We recursively sort this, which means we pick the value x. It's the first element. That's 1. We extract all the things that are smaller than 1. That's an empty list. That immediately returns. And then we extract all of the things that are bigger than 1. That's 2, 3, 4, 5, up to 1999. So am I going to have room to finish this on this page? Nope. Because really, it's going to look like this. Nothing here. And you see the pattern, right? This one had 2,000 elements. This one's going to have 1999 elements. This one's going to have 1998 elements. This one's going to have 1997, 1996. It's not the number of these things it's not the sizes of these lists that are important. It's actually the fact that we're going to have to keep recursing on this thing until we get down to 1. And we already saw that Python won't let you have a recursion depth that is more than 1,000 deep, and this is trying to go about 2,000 deep. And that's why we get that crash. You can see it here. It's telling us where it happened by showing us all the functions that were called leading up to this crash. And yeah, all of those functions are quicksort, quicksort, quicksort 995 times, or 996. So that's when the crash happens. So maybe it's not such a good sorting algorithm. I mean, it seemed to work really fast for a random array, but when the thing was sort of randomly ordered. But when it's sorted, well, two things happen. A, it crashes, and B, even if it didn't crash, it would run really, really slowly. Because imagine that I gave it a million elements to sort. well, then it would split that into two lists, one that contains 0 elements and one that contains 1,000,000 minus 1. And then, so that it just made a whole new list of length 1,000,000 minus 1. And then when it works on that, it'll make a whole new list of length 1,000,000 minus 2. And a whole new list of length 1,000,000 minus 3. And so if you add all that up, that ends up being a number that looks something like this. So that would take too long, right? This is, this thing here is, billions when you have 9 zeros, so we're talking about 1,000 billion, so 1 trillion. That would be creating about lists that contain 1 trillion things. That's too slow. Okay, now here's the really clever thing, and this is like reaching. I mean, it's super simple to explain, and you guys will understand it, but it touches very, very deeply on really deep concepts in computer science and in theoretical computer science. Is there anything we can do to fix this? So that if I give it a sorted array or something that looks kind of sorted, that it'll still run fast? Yeah? The middle element. So you mean something like that?
Yeah.
So we can do that. Let's even go up to, feeling confident, we'll go up to 100,000. And that's really fast. Is that always going to work? Yeah.
Sorry, I don't know, but if all the list elements are the same thing.
Okay, so let's say A is equal to 1 times 100,000. So A is just a copy of all ones. Super fast. So what happens in that case is you pick the 1, you split the list into the stuff that's smaller than 1, that's empty and it returns immediately. Then the list that contains all the ones, that one you don't recurse on because it's already sorted, and then the list that contains stuff bigger than 1, but that's empty and it's immediately. So that's somehow the fastest thing for this thing. But this choice here, choosing the length of A divided by 2, it seems to look good, and it works in the case where this data is sorted, but I mean, there is still a way to break that. It just takes a list which is not the one that you would sort of naturally think of, but I can always say that my list will always contain the elements, or I'll make you a list that contains 0 up to n minus 1. And right here at position, this would be n divided by 2, I'll put the value 0. And so, so then you pick that, and you end up recursing on the rest of the thing. And now, watch what the algorithm is going to pick next. That's where I'll put the value 1. And so that won't work. So there's actually, this was a good idea, changing the element you pick, but the really deep thing here is, I think we can, I don't pick the first one, I don't pick the middle one, I don't pick the last one. Instead, I just pick one completely at random. And that choice that I make, it has nothing to do with what's in the list. It didn't even look at what's in the list. So in particular, there's nobody who can make a bad list that affects that choice because I didn't even look at the list when I made that choice. So let's go back to our bad-looking list. A. And now it's fast again. And that's true even if I make a bad-looking list of length 1,000,000. That'll take about 5 seconds, like it was taking before. So the sort of deep lesson here that you will come back to later in your studies if you continue to study computer science is that sometimes a random choice like this is the best thing you can do. It foils anybody who's thinking of ways to break your algorithm because they can't design in this case, a bad list that's difficult for you to sort because they don't know what your algorithm is going to do ahead of time. Right? They can design, a list that looks like this, that puts the 0 in this spot, but you're unlikely to pick that particular spot. So indeed, this use of randomization gives you a robust algorithm that sorts quickly, and the name quicksort really is applicable here. Okay. So questions about quicksort? All right. So here's another problem that we can maybe solve sort of almost by magic. Suppose I give you a list, and here I'll put 3 elements in it, maybe A, B, and C. And I want to compute what's called the power set of this list. What's the power set? Well, that means I take every possible choice of subsets of things in here. So for example, the power set of the list that contains A, B, C, well, I can choose not to take A, not to take B, and not to take C. Then I'll get the empty list. Or I might only take A. Or I might only take B. Or I might only take C. Or I might take A and B, or I might take A and C, or I might take B and C, or I might take A, B, and C. So this is, if I say, ask for the power set of this list, what I should get back is a list that contains all of these lists. The empty one, the one that contains A, B, the one that contains C, the one that contains AB, the one that contains AC, the one that contains BC, and the one that contains ABC. So this particular power set has 8 elements in it. That's not an accident. Anytime I take a list of size 3, its power set will have 8 elements. Anybody know if I take a list of size 4, how big the power set will be? It'll have 16 elements. Why? Intuition? 2 to the power of 3, 2 to the power of 4. What's the 2 coming from? So the 2 is coming from this decision of, for each element, I get to choose if it's in the set or it's not in the set. So there's 2 choices for each element, and so if I have 4 elements, that's 2 times 2 times 2 times 2 choices is 16. If I have 3 elements, it's 2 times 2 times 2. So let's see if we can write a function that computes these power sets for us. And of course, we want to use recursion. So, what is, we've always got the two things we need to consider, the easy case, the base case, and then the recursive breakdown. So what is the easy case for powerset? If you give me an empty set, then it only has sort of one thing, and that's the empty set. I mean, there's no choices. What subsets of the empty set are there? Well, there's only one subset, and it's the empty set itself. Okay, so if the length of A is equal to 0, then what I should return is, now remember, what I'm supposed to be returning here is a list containing these lists, which are subsets of this thing. So in this case, I'm returning a list that contains one list, this empty list. Okay? All right. That looks like it should work. How do I break this into a smaller problem? Well, we can always try the typical strategy, which is just to take a little nibble out of A. So let's say, let's just bite off the first element from A. So in this case, that would be biting off this piece. Let's recurse on that part. Okay, so if I did that in this example, and A was a bad choice here, but let's stick with it anyway. I've got x equals A, and I recurse on BC. And now this is recursion, so I can magically assume that what comes back from that is the right answer for that sub-problem, BC. So what comes back from there, so PS is, it will contain the empty set, it will contain the set that contains A, the set that contains B, the set that contains C, and the one that contains B and C. So that's what will come back in this example. Now how can I turn that into a solution for the whole problem? So if we think about it in terms of that first element, x, the first one that we pick out of the array, just in terms of that first element, there's two kinds of sets. There's the sets that don't contain x, and there's the sets that do contain x. So in this example, where these things were A, B, and C, and so x is equal to A, when I recurse on BC, I get back these things. Are these sets that contain A or sets that don't contain A? They don't contain A. I don't see A anywhere in this picture. Is this all the sets that don't contain A? Yep. It's definitely all the sets that don't contain A, because once we decide not to put A in, then all we can get is all the subsets of what remains, in this case B and C. So I already have somehow half of my solution here. This is already half the solution. This is all the sets that don't contain A. Now all I need is all the sets that do contain A. Well, what do those look like? Well, don't those just look like this? Isn't that then all the sets that do contain A? I just take every set that doesn't contain A and add A to it, and now I get all the sets that do contain A. And so that means since there were only two kinds of sets, the ones that do contain A and the ones that don't, now I have all the possible sets there are. Let's see how we implement that. So I've already got this thing. So that's PS, the power set of things that don't contain the value, the first element that was in my list, which I'm calling X in this example. And now all I want is another one, which is, how do I want to do this? I'll say X plus B for B in PS. Okay. So PS is a list of lists. For each of those lists, I'll just add that, prepend that first element onto that list and get this second part of this thing. Okay? And then finally, what I want to return is, let's start with the ones that don't contain the first element, and then the ones that do contain the first element. See if that works. One, two, three, four, five, six, 7, 8. Again, it's really almost like magic. It's not, what it is actually crystal clear thinking about the problem and how to express it in terms of something smaller. It's not at all magic. It's induction, and that requires some very clear thinking, but in the end, it's actually simple code. That clear? And if I ask for the power set 1, 2, 3, 4, I get something with 16 values, 5, 32 values, 6, and so on. So there's a few things you can learn from this. One is, okay, here's the how you make power sets. But also we define them sort of recursively. And somebody said, well, the number of, if the list A has length 4, then the power set should have 2 to the 4 things, and if it has length 5, it should have 2 to the 5 things. We can kind of see why that's happening now, right? So what happens is if you give me a list of length n, the first thing I do is take the power set on a list of length n minus 1, and the result is then twice as long as that thing. So that's why you get 2 to the n. All right. Think we can take the power set of a really long list? So I can tell you we won't be able to take the power set of a list of length more than 1,000, because this is following that recipe that doesn't work so well, right? It just nibbles off the first value in the list and then recurses on the rest of it. So it would give us a recursion depth of 1,000. But before that, well, actually that will be the problem, but we would have another problem, which is that the power set of a list of length 1,000 would have 2 to the 1,000 elements in it. And again, this is a number that's more than the number of atoms in the universe. So we certainly couldn't store this list because we couldn't make enough memory cells to actually store this list. There's not enough matter in the universe to do that. So in this case, it's okay that we do this sort of this nibbling thing, because if someone asks us for the power set of a big list, it's hopeless anyway. But we'll never be able to give them a power set of a list with more than 1,000 things. Okay. Questions there? Okay. So, here's another one. Anybody ever heard of Fibonacci numbers? So what are the Fibonacci numbers? Or what's the biological experiment that they're supposed to represent, if you don't know the exact definition? Nobody knows what Fibonacci was studying? It's the most interesting part of the story. It's about sex, right? I mean, it's Fibonacci numbers are supposed to represent the number of rabbits after n generations of rabbits mating. So you start with a couple of rabbits, and then they make a couple of rabbits, and then those two mate with the previous two generations, and so on. And so the idea is that you get a lot of rabbits in a very short number of generations. So let's take a look. If we don't know what something is, we can always look it up. Not math is fun. Wikipedia. Okay, so we get a nice definition from Wikipedia, which is that Fibonacci number 0 is 0, Fibonacci number 1 is 1, and Fibonacci number n is n minus 1 plus f of n minus 2. This, in the version with rabbits, this 0 doesn't make sense, because in that case we would only have one rabbit that can't mate with itself. In the version with rabbits, it starts with f of 1 and f of 2. But nicely, this gives us the definition. In fact, it gives us the recursive definition. So Fibonacci of 0 is 0, Fibonacci of 1 is 1. So that we know how to implement. If n equals 0, well, let me shortcut it. If n is less than or equal to 1, return n. So if n is 0, return 0. If n is 1, return 1. And otherwise, f of n is f of n minus 1 plus f of n minus 2. So Fibonacci of n minus 1 plus Fibonacci of n minus 2. Fibonacci of 0 is 0, Fibonacci of 1 is 1, Fibonacci of 2 is 1, Fibonacci of 3 is 2. And let's see some, I don't know, let's try Fibonacci of 10. 55, not too bad. Fibonacci of 100. That takes a while. Let's try not to be so greedy. What about Fibonacci of 15? 610. Let's try Fibonacci of 20. 6,000. 25. Now we're up to 75,000. Now we're up to 832,000. It's a lot of rabbits. Okay, so that gives us you know, we can get up to Fibonacci of 30, and maybe we can even get up to Fibonacci of 35, maybe after a little while it might show up for us. But there you go. So it's a little more than 9 million. But it seems to be slow, right? This is taking time. So let's think then. So I mean, this is basically the definition of Fibonacci numbers, just recursive implementation based right on the definition. But is there maybe another more straightforward way to compute them? Maybe without recursion? Well, let's try. Let's just try and unravel things. So in order to compute Fibonacci of n, I need to know Fibonacci of n minus 1 and Fibonacci of n minus 2. But in order to know Fibonacci of n minus 1, I need to know Fibonacci of n minus 2 and n minus 3. And then in order to know n minus 2, I need to know n minus 3 and n minus 4. So maybe it's better to start at the beginning with things that I do know and work my way upwards. So let's create a list. And I have to put something in there, so let's make that a list of length n plus 1, full of zeros. Okay. And let's call it f, because it's supposed to represent the Fibonacci numbers. So make f at I be f sub I, the ith Fibonacci number. So we already have this. F at 0 is equal to 0 at this point, but we should do f at 1 equal to 1. And now that I have 0 and 1 set up, I should be able to compute f of 2, right? So if I take I equals 2, then f at I is equal to f at I minus 1 plus f at I minus 2. For I equals 2, that's going to work, because then I minus 1 is 1 and I minus 2 is 0, and both of those things are the correct values. So that will give it to me right now for I equals 2. But then once I've done I equals 2, then I can do I equals 3, because I'll have the values that I need for that. And once I do I equals 3, I can do I equals 4, because I'll have the values that I need for that. So really, for I in range, we start at 2, and we go all the way up to n, and we just apply that formula. The difference is now we're not applying it recursively, we're applying it to values that we've already computed. They're just sitting there in a list. And then finally, we return f at n. Let's try that. So Fibonacci 2, what did I say? What did I do wrong there? There it is. I'd better do this with a list of at length at least 2. Otherwise, I won't be able to get Fibonacci of 0. Okay. So that's 0, 1, 2, 3, 4, oops. 5. Okay, and let's compare some of the bigger ones with what we had before. So 15 should be 610. 610. Good. So we'll kill this print statement. So Fibonacci of 35, we already computed that, and that was this about 9.2 million, nearly 9.3 million. And there it is again. And Fibonacci 100 is the one that we got stuck on. Now it comes back instantly. What about Fibonacci of 1,000? That comes back instantly as well. 10,000? That also happens really fast. But the original one, the recursive version of Fibonacci, already for 35, it takes about 5 seconds. And for 40, I suspect it will take about 50 seconds. Why is one of these things so much faster than the other? They both compute the same thing. You might have thought that, okay, maybe Fibonacci, it was slow when you make, Fibonacci of n is slow when you make n big because it's a big number. But the numbers aren't that big, right? I mean, 9 million is not such a huge number. In fact, we saw that the second version can compute an enormous number, that number that has like 300 digits in a fraction of a second. There we go. Fibonacci of 40 finally returned. It's about 100 million. But that took nearly a minute to do. So what's happening? Why is one of these so slow and the other one not? Well, to understand why the second one is not slow, I mean, it's not hard to see, right? All we do is we create a list of length n, or length n plus 1, and we fill it out with a for loop. We just scan through that list. So scanning through a list of 1,000 things, that doesn't take long at all. I mean, we've done that many times. In fact, we just sorted a list of 1,000,000 things, and that only took a few seconds. So that's no difficulty there. So that's why the second one is so fast. The really interesting question is, why was the first one so incredibly slow? And to understand that, well, we only have to try and do a few small examples. So let's say I want to compute Fibonacci of 4. Well, to compute Fibonacci of 4, I need to compute Fibonacci of 3. And to compute Fibonacci of 3, I need to compute Fibonacci of 2. And to compute Fibonacci of 2, I need to compute Fibonacci of 1. And Fibonacci of 1 is something I know how to compute. It's the base case, and the answer is 1. But I'm not done yet, because to compute Fibonacci of 2, I don't just need Fibonacci of 1, I also need Fibonacci of 0, which comes back as a 0. Now I'm done computing Fibonacci of 2. I give that back. The answer is 1. But I'm not done computing Fibonacci of 3 yet, because to do that, I also need Fibonacci of 1. That comes back fairly quickly. The answer is, or it comes back immediately. The answer is 1. And this thing is now done. It returns its answer of 3. But to compute the Fibonacci of 4, I'm still not done. I needed 3, but I also need 2. And what does 2 look like? Well, I've already seen what 2 looks like. It looks like this. So there's a 1 and a 0. And that returns a 1. And then finally, Fibonacci of 4 says, okay, I can return 3 now. Okay, that seems kind of slow, and you see also maybe kind of dumb, because it just did a whole sort of computation twice. At some point over here, it computed Fibonacci of 2 because it was trying to compute Fibonacci of 3, and over here it computed Fibonacci of 2 because it was trying to compute Fibonacci of 4. Should have only done that once. So there's where somehow the inefficiency is coming from. But there's a bigger way to see this. If I look at this thing, so this is what's called the recursion tree, and it's really just the pictures of the stack as it evolves over time. But the important thing are these base cases here. So that's these things here. This is where we reach the bottom and we don't recurse anymore, we just return an answer. Now, in the base cases, what is the answer that we return? It's either 0 or 1. Okay? So, all of these base cases, they either return 0 or 1. If this thing is labeled with a 0, it returns 0. If it's labeled with a 1, it returns 1. And what comes out at the top here? Well, what came out is the number 3. Why the number 3? Well, because there was a 1 that popped up from here, and there was a 1 that popped up from here, and there's a 1 that popped up from here. And eventually all of those come together and they come out at the top. And in fact, a sort of another way to see what number is going to come out at the top is you draw this whole tree. You look at the leaves that have 1 and the leaves that have zeros, or more importantly, these base cases, which we'll call leaves. They are labeled with 1s. Each of those returns a 1, and at the end, all that comes out is the sum of all those 1s. So that means when I ask you for Fibonacci of 40, and the answer is 100 million, what does this picture look like? So this is supposed to be the execution of this thing. Well, this picture is one of these giant things with all of these things hanging off the bottom, and what pops out the top is something like 100 million. But where did this 100 million come from? Well, it came up one at a time from the leaves here that were labeled 1. So that means in order to get 100 million, I had to make at least 100 million recursive calls on problems of size 1. So the reason this recursive thing is so slow, it's yes, because this number is big, but the recursive algorithm, it can only make big numbers by adding up a whole bunch of 1s. So really, this thing, in the end, did an addition, which was 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, 100 million times. That's why it's slow. So you have to be a little bit careful with recursion this way. Sometimes there's sort of a nice natural solution, recursive solution that just jumps out at you. Like, for example, when someone defines the Fibonacci numbers, you think, oh, I'll implement it recursively, and you get something terribly slow. And then you have to think about why that happened and whether you can fix it or not. And then on the other hand, sometimes somebody gives you a problem that looks like it has nothing to do with recursion, like sorting, and you find a recursive solution, and it comes out to be incredibly fast. Much faster than you would have expected. So, I mean, these are sort of big lessons that if you continue to study computer science, these are the kinds of things that you study. Things like, these recursive algorithms. how long do they take? How do we determine if they're fast or slow? What are the sort of the general rules? But now I think I'm sort of giving you a teaser for, that there's a lot more going on under the hood here that's worth studying. We won't do too much of it in this class. We'll start next week with a guest lecturer who will talk a bit about algorithms and efficiency and sort of estimating efficiency. But I hope that what I've shown you today gives you an idea that this is it's a non-trivial topic, and in fact, it's basically what I do as my line of research these days, is to study efficiency of algorithms. Okay, so that's a good place to close off for today.